Okay, so today we're first going to talk about AutoFSDP. So, Wei, I think you're the most logical person to sort of lay out the problem to start.
Sure, sure. I can share my screen. Can you see the screen?
Yes.
Yes. So 1 minute recap of the problem. So in FSDP, considering we have a module, right before we are doing the forward, we need to all gather the parameters. So there's a compute time for the module. There's a communication time for the module. So we need to decide the wrapping so that the communication and the compute can overlap. So the best strategy is to, if the grouping is too small, then the compute will be exposed. Otherwise, the if the grouping is too large, it will be a memory issue. So that's the recap. For people with FSDP background, the problem goes with this. So considering we have a model, either it's internal or external, do we have full graph compilation to resolve the problem? If yes, we apply torch compile, zero graph break, then I think the solution would be simple FSDP. We do the parameter bracketing inside inductor, treat it as optimization. If no, then that's what we are talking about today. If there's even one graph break, we cannot see the full graph at the inductor level, and then we need to think about the bucketing and estimate the runtime with some part of the region is compiled, with some part of the region in eager. That's where the difficulty come from. And that's about the AutoFSDP we are talking about. Questions on the framing?
Yeah, I have one. Can you hear me?
Yes,
Yeah.
we can hear you.
So the what happens with graph breaks in this case? Do you have multiple graphs that get orchestrated on the eager side for the prefetch and so on of all of the FSDP, or is it all going to be embedded into the graph somehow?
Right. So this is like estimate the how the runtime, right? But if I'm thinking about workflow like this. First, estimate the FSDP policy for one time before the training, and for all the future trainings, use that policy to run it. And we can do the torch compile for the compute part only and ignore the FSDP hooks.
Sorry,
Okay,
Francesco,
so
yeah, go ahead.
I'm not sure it's fully clear. Are we assuming we have like the
Okay, Francesco, let me try
like,
to answer your question.
yeah.
The regime Wei is trying to deal with here does involve graph breaks. So he is not going to make assumptions that he has the entire graph before making bucketing decisions.
Yes, and then it's almost as if it was basically eager, but some small parts within a graph break might have been compiled, but it's basically eager mode only,
Basically
right?
eager mode, yep.
Okay.
Actually, let me call on Jansel for a moment. Jansel, did that motivation make sense to you? Because we have talked about this, and you're like, well, I think I need a little more convincing about this use case.
I mean, the main thing I'm worried about is just fragmentation here. Like a distributed that's already super fragmented, we already have lots of ways of doing things, and like I just worry that this is more fragmentation.
Wei, do you have anything to say about that?
Yeah, I think the fundamental thing is, do we care about graph break case? We can claim that we do not need support this case, and then we can avoid the fragmentation. But I think for internal and external, like AWS, I think it's quite hard to commit zero graph break for the users.
Yeah, I mean the other way to support that would be to try to use the existing FSDP rather than creating something new, and just make that work with compile.
But wait, you are using existing FSDP,
Yeah,
right?
yeah. So the estimating the FSDP bucketing is orthogonal to FSDP. So we have the FSDP policy, then we can use it as input for existing FSDP.
Okay, why don't you carry on?
Yeah. Okay. So I think that's where we the problem is like with one more plus graph break. I think right now, as of today, like how do we make this work in eager? So this to set a context, we have fake tensor mode, we have runtime estimator, and we dispatch. We observe all the tensor ops at the torch dispatch mode, and we estimate the runtime with the bandwidth and the flops. That's the current status. Questions here?
So once you get the per operator estimates, you need to have an estimate for the peak memory.
Yes.
Used by a given configuration.
Yes.
Are you going to be discussing about that afterwards or not?
Memory is estimated similarly using the torch dispatch mode and the module tracker. I didn't list the memory example code, but it's the tracing mechanism is very similar.
Yeah, but what I mean is that, yes, you can measure the memory for a given operator, but whenever you want to perform a global optimization, like the one you're going to do here, you're going to also need to take into account the fact that during backward propagation, you're going to be keeping some intermediates around, and that can basically increase your memory usage, right? And you need to either you model that explicitly or you forget about that. Just I wanted to understand if you were planning on modeling that.
Yeah. So yes. So we are also well, for eager, we do have a script in Torch Titan that trace both forward and backward, and also the activation memory. So yes, the answer is yes. In eager, we want to model that.
All right, I have a question then. Can you like briefly describe how the memory usage estimator torch dispatch mode works? Just like a high level like description about like what it does.
I think the work really roots in San Francisco's the SAC work. So we track. So we split operator into like, is it random? Is it view? Is it like actually generating a new memory? And then we have a module tracker, so we can always attribute the memory to the module level, and we trace the. We also keep track of the activation memory, and then from forward to backward, we record the peak memory.
So let me just try to get a little more detail here. So essentially, your torch dispatch mode, for every output, you add that to your like memory that is in use, and then when tensors get deallocated, you remove them from the memory in use, something like that?
I think that's close. Yeah.
No.
I'm not,
I want to know exactly because
Yeah.
another way, which sort of sounded like what you were describing, is you trace the forward and backwards graph, and then you have some like FX analysis that tallies the memory usage on the graph.
So yeah, on some Discape, I don't think we have like effect graph like analysis here. I think it's purely module tracker and add and minus that memory from that module. And
So more
yeah.
concretely, how do I know when something's not being used anymore so I can just subtract it from the memory usage?
I think maybe I might be wrong here, but given that you mentioned the SAC work, maybe what's happening is that whenever you have the output of a module or an operator, you add that memory to the associated hierarchy of modules in the forward pass, basically. So just keep adding, assuming that everything which is an output of an operator is going to be saved for backwards. So it's going to contribute to the memory, right? Yeah. Now, the question is less clear about the backward pass, though. And that's why I'm not, I was asking the question because I'm not super clear there.
Yeah. So I need to do more homework on this. I think this is the backward is the missing part. I might have gap in understanding this part of the because I picked it up from Sankit. I think this is also a gap on my side.
Francesco, I have a question for you then, which is, in principle, do you believe that like we could simulate a run and calc the peak memory? Even if it maybe isn't implemented exactly correctly, does this feel in principle something you can do?
So it is something, supposing a model where I have full graph and everything. That was the case I was thinking about. And you have things like activation checkpointing on top. It can be slightly tricky because there are multiple possible permutations of your backwards graph that are valid, but they have different peak memory usages. So it's a fairly big, like you can formulate that with a linear program or something, or integer program, but it gets pretty big. Feasible if you have the full graph, yes, but it's not easy. Complexity is gonna blow up if you just do it like now, because the thing is the ordering of execution matters whenever you're taking a decision, and the ordering matters, and it changes depending on your grouping policy. Is it clear what I mean?
Yeah, that makes sense.
Oh.
But let me try to make it easier. So if somehow I know exactly the order I run things in, then you would agree that I can compute the peak memory.
Yes.
Okay.
But then you need to, yes. In this case, yes.
Right, but you're sort of like thinking ahead. You're like, oh, I want to find the best schedule subject to like not blowing out my peak memory, mumble, and that is not that we haven't figured out yet. Okay.
And that is without considering AC, because if you add AC in the story, then you can actually recompute from the last activation, right? So we need to basically not just follow the forward then backward order on your backward pass.
Okay, Wei, I think that's enough for this topic for now. Do you want to keep going?
Yeah, sure. I think the difficulty really appears when we are considering graph break case. So the feedback is No, eager is not good. We are doing the runtime estimation because we are not considering the fusion. So in real production, what they want is, say we have a compiled region, how can we estimate the runtime for the fused ops? And then when we switch to eager region, can we resume our previous solution for eager, which is using torch dispatch mode? And then we come back to compiled region. I think it's the switching that is very hard here. So right now, in my mind, it's like once we do graph break, let's resume the torch dispatch mode and disable it. Questions?
Yeah, so is it fair to assume that anything compiled is going to be faster than not compiled?
Yes, and the memory bandwidth is also going to change.
Yeah. So if we do the analysis supposing eager code, then that means that our compute estimate is going to be an upper bound, right?
Yes.
To be clear, Wei wants to like actually have accurate numbers for the compiled regions. So that's where we're headed.
But my question is actually, is it actually necessary? Like, okay, the runtime can go to 0, but can't you just add a offset or something, like say multiply something by a less than 1 or greater than 1 factor? That will basically put you in a overly optimistic or overly cautious setup for eager while working for compile, roughly.
So that's an empirical ratio we can apply to the eager runtime, right? You are thinking about one empirical ratio.
Yes, I mean, if on average, Torch compile makes models 1.2 or 1.4 times faster, we can just put that scaling factor there.
Yeah, I think this is something that's very practical, and that's also the thing we want to try before actually resolve the post-compile problem. It's just I think like our customer is asking for the North Star, like which is actually understanding the post-compile. That's why like we want to discuss further.
Yes, I just wanted to understand if the North Star is actually trying to make this system which reasons in eager, but taking some information from potentially compile, is the North Star, or instead working on removing the graph breaks and reasoning on the no graph break scenario? That would be my question here.
I think for internal like customer, the very head customer, yes, removing graph break is a road. It's just that when we release this to OSS, I don't think that's an option because we do not have control.
I want to call on Jansel again because I think this kind of gets to the heart of like the cost benefit question you were asking earlier.
Down here.
We can hear you.
Oh, can you hear me now?
Yes.
What were you hoping for me to comment on?
So we've been basically like Francesco posed the very reasonable question, which is instead of spending all this effort building this complicated graph break aware and compile aware North Star, maybe the North Star should just be no graph breaks.
I think that's a valid point because, like, especially for FSDP, like the place where FSDP really makes sense is at a level of scale where like people are willing to put in a lot more work than they are in sort of like if they're just using DDP or something small or just single node. And so sort of given that we have sort of like a customer segment here who's, you know, more tolerant to putting in work, asking them to just go and fix the graph breaks or sort of wrap the stuff or wrap stuff in custom ops, which is probably where most of that work comes, doesn't seem like that onerous in this specific use case.
Francesco?
Yeah, I mean, I think that also aligns with my expectations because the so I think the solutions we can actually give, so assuming graph breaks and Gauge compile and so on, it's like an improved version of what you could potentially get in Eager, but there's only so much we can do by eagerly tracing the code, right? And I think maybe a bunch of the graph breaks can actually be overcome by influencing people on how to do things differently. People have been following patterns on how to implement things, and maybe if you just switch and teach them, hey, look, Torch Titan, for example, you can get away with A, B, and C by doing like this. And people are going to follow that pattern, and that pattern is going to be potentially graph break free. And same thing for internal customers, where we can basically evangelize potentially a PT2 compatible way of writing models. That's not going to be too different from what they do already, maybe even easier. Because I think what the problem that happens is that we start adding too much eager-only optimizations to our code that then makes the life of compile and everything else harder. So maybe you should just like go back in time, make things simple again, and then in that simple scenario, we can actually trace and compile and get the full graph more easily. And in there, you can actually reason globally about the model, and then basically send FX graphs to every researcher in optimization that we know, and ask them to get algorithms for optimizing communication, compute, and so on.
Well, I think one different thing is I'm assuming the graph break is coming from the compute itself. I'm not actually assuming the graph break comes from the FSDP hooks. So yeah, it's actually okay to not compile FSDP hooks.
Yeah.
Is that sort of like missing the like? I guess the question is like can we ask users to just fix their graph breaks if they want to do distributed at a very large scale? And we can, if that's like an acceptable requirement, which I think in general for PyTorch, like it's not, but like for the specific use case of like, I want to scale to, tens or hundreds of thousands of GPUs, if you're sort of operating at a very large scale, I think saying like, hey, you got to go fix your graph breaks is a totally reasonable ask. And if that's true, then we should then we can potentially have like a much simpler solution.
I want to solicit some comments from the other side of the fence. Wolfung, can you weigh in as someone more like you, because you have also cared a lot about handling graph breaks for like the sort of Rexy style use cases?
Yeah. I mean, I think I see Jason's point. If people are spending a lot of money training large models, they should be able to spend time fixing graph breaks. But I think where the cliff is when people newly develop a model and then they try to apply FSDP the first time, and then they will hit the price of needing to fix graph breaks. I think that's where the pain point will mostly be. Like we'll probably expect like people complaining on Twitter saying, "Oh, applying FSDP doesn't work because all the graph breaks, and I don't know how to fix them." Like
okay, let me try to make this argument stronger, because that's not what we said, right? FSDP will work. You just won't get this fancy auto bucketing optimization, which is the point of AutoFSDP. Do you think you can respond to that?
Yeah, I think that would be okay if we don't have the optimization.
Horace? You're muted, Horace. Francesco, do you have a
sorry.
hand?
Can you hear me?
Oh, yeah, we can hear you now.
Like I guess this general framing doesn't really like make that much sense to me, because I don't think people training at large scale are going to be using like AutoFSDP anyways. Like I don't think this is really a particularly compelling offering for, say, like Llama or something like that. And so like the target audience for this is really like kind of people who are training at somewhat large scale, but are they're willing to like give up all their optimizations like to us, and not really like the people who are actually training at like 100,000 GPU scale.
Help me understand. So are you saying that we should be more... Is this a claim in favor of AutoFSDP or against?
Well, I think my claim is that like whether you can tolerate graph breaks or not is a little bit more subtle than just are people willing to put in the effort or not. And sometimes I think of it a little bit as like a bell curve effect, where it's like, you know, if somebody wants to put in like zero effort, then we want to support graph breaks, because, you know, like that's what you'll get if you just compile code that, you know, like arbitrary user code. On the other hand, if the users are willing to put in like a ton of effort, then they probably will want to end up doing customizations that like do not apply, like that we cannot really like fit into our graph. So for example, like the pipeline parallelism stuff that people are doing internally, like I have no idea how, like I don't really even have like understanding of how we can fit this AutoFSDP in combination with pipeline parallelism. And so, you know, like that's just kind of like a non-starter for using AutoFSDP for super large scale training.
Francesco?
I mean, if this type of approach is just a non-starter for large scale training, that's like that like maybe that means we're building the wrong thing. Maybe we need to build something more hackable, where like rather than being sort of just this like you're either in auto mode or entirely manual, like maybe we could build something where you use the automatic thing to generate sort of like a schedule which you can then hack on manually, and you could use it sort of as a starting point or as like a reference. Like maybe we're just this is just a sign that we're like building the wrong product.
Well, like in this case, or like I'm kind of sympathetic to that, but I do think there is like a customer for AutoFSDP here, right? Like there are people who basically just want to be like, okay, I don't really understand parallelism, I don't really understand, you know, FSDP. I just want you to take my model and, you know, I want to run it on a lot of GPUs, and please make it as fast as possible. And like for these kind of customers are the type of customers that I think like AutoFSDP is like most compelling for. And to be clear, like this is like a very real customer segment. Like, you know, you start wanting to use, like I don't really think it's true that FSDP is only for like super large scale trainers. I mean, like nowadays, like 7B would be considered like a pretty small model, and already at 7B, like you most likely want like FSDP. And you know, there's a ton of people who are like running or like training small like 7B models on their GPUs.
Yeah, but all of those 7B models people are training are basically just the same Llama or variants of Llama transformer models, right? That they can basically copy paste, and they're gonna be full graph or.
Oh no! I'm saying like for those customers, I think AutoFSDP is a super great fit. Like
Yes.
I think like the median customer that I imagine for AutoFSDP that's like where this makes the most sense for them is like a researcher who wants to try like maybe a Llama scale model at some like with some twists. You know, I don't know, like maybe some different data, a different attention mechanism, maybe like a slightly different change of the architecture, and they don't really super understand parallelism. They just want to run their model at like, you know, maybe even like 1,000 GPUs, like, you know, something like that scale. And yeah, and you know, they don't have like a lot of like engineering support. And so for those people, they want something like AutoFSDP. They want something where they can just like set it, be like, okay, you know, you guys, you know, PyTorch team is doing, you know, as best of a job as they can, and it's just gonna make our stuff as fast as possible.
I think maybe I have a question here, which is, we are talking about FSDP, but we didn't think about or didn't mention about like AutoDDP, where we find the right bucket and size to whatever, right? I mean, and the thing is, FSDP is a bit more complicated variant of DDP, but it shouldn't be its own like completely new variant, because if the person also wants to use tensor parallel or something else, well, that is not going to be taken into account there. And for like slightly larger models like 7B, maybe a bit more, you might need to have other variants of parallelism as well, right? So the thing is FSDP just enough for those customers, or they're going to have to go and plug in all of the other variants as well, in which case, well, we're not going to be providing a solution to them either.
Yeah, I think that's also a good point. Like I think that like a solution that is too optimized towards just building like automating FSTP for these kind of customers, I don't think is super compelling.
I want to throw my head in for why this market group makes sense. So we talked a lot about Llama, but in recommendation system space, which is really where like the original ask for this came from, it's very common to have people doing all sorts of weird modeling things and to not have actually managed to make their graph, be a single graph. In fact, if I don't remember if FSDP goes over the sparse arc, but like getting the sparse arc to be a single graph, quite difficult. Like we think it is possible, but we have spent quite a lot of time and effort on it. So
yeah, I actually just discussed with someone, and the sparse arch doesn't actually use FSDP. It's only the dense arch.
So that helps quite a bit.
Yeah.
I guess like I think I'm definitely convinced that there's like a market for people who just like want to go auto distributed. But I think that I don't think that what they want is auto FSDP. I think they want something more general. They want you just like take my model, make it go distributed, figure out whether it's DDP, FSDP, whether it's like whether there needs to be pipelining. Like it's sort of like a more like this seems too narrow for sort of the automatic thing, because like it really depends on the model, like and the scale, like what type of parallelism makes sense. I also worry that we're creating this cliff where people at the sort of like small and medium scale can use the automatic thing, but then if they want to like grow and sort of scale up, like they're going to hit this wall where sort of the automatic thing stops working, and in order to actually reach the next level of scale, they're going to need to throw out the automatic thing entirely and start over. And I wonder, like, is there a way we can create something a little bit more hackable, where they can sort of gradually wean themselves off the automatic stuff, and or maybe sort of make that transition from the small and medium scale to the large scale easier.
I do have one proposal. Sorry, maybe you can cut me.
Let me do a moderating. So, Wei, I think we have some parts of your proposal that are like not FSDP specific, but more about like understanding the flop and memory bandwidth behaviors of compile. Maybe you should present that, and we can talk about it.
Or, sorry, I guess I am a little bit confused why that is hard.
I mean, it's annoying. Like it's certainly not trivial.
Or like I feel like we already have like a runtime estimation thing in Docker.
We do, but how do I use it?
You call like graph.scheduler runtime or something like this.
Yeah, I can say about I can explain the blockers. I think there are generally three things that is considered big mountain. The first thing is how to map the tensor ops at the inductor level back to the NN module. So we know that, hey, inductor give this tensor ops this estimation, and then can we mapping the estimation back to the module? The second thing is torch compile. When we go from torch compile to graph break, and to a eager region, can we resume the torch dispatch mode so we can continue observe the runtime for the eager part? The next thing is fake tensor mode for torch compile. Fake tensor mode is a requirement because we kind of want to avoid real GPUs. Imagine you launch a job on 1K GPU. If we really want to tune this auto bucketing without fake tensor, we tune this by running on real GPUs every time and iterate, and that's kind of pain. So those three things.
These seem like reasonable asks, actually. Like many of these seem like things that I would want for other things. Do we have comments, questions on these asks?
I'm sorry. What were there was like map runtime to modules and
yeah, because like FSDP and potentially other things don't care about the individual operators, but they want to know where the cost buckets to the actual modules because they want to interact on a module basis. The torch dispatch mode, torch compile is a sort of like mechanical difficulty, which is they have this thing that works in eager mode with torch dispatch mode, but you need something else to happen when you hit the compile regions. And the fake tensor mode is just we want to compile the inductor stuff so we can get the scheduler information, but without actually having all the real tensors because we want to simulate a big run on less GPUs. NYC.
Two questions. So one is on the like disabling torch dispatch mode during compile. That seems reasonable. It's also just like a semantics change from what we do today, which is we say like we haven't defined what the semantics of torch dispatch mode under compile are, and therefore we just always graph break on it. And like you could imagine an alternative where we say that the way we handle torch dispatch mode is similar to how we handle torch dispatch subclasses, which is like tracing through them at compile time. And in practice, it seems like there aren't that many use cases for that, and the like clock counter mode and sort of like runtime tracking stuff seems more common for modes. So it feels reasonable. I guess I'm just calling out that it's like a change from, or it's sort of like agreeing on behavior for how torch dispatch mode works in compile.
One thing I will say is that I don't think this behavior is correct for all torch dispatch modes. For flop count specifically, I think this is the right thing to do. But it just
I don't even agree that it's necessarily the right thing to do for like flop, or like.
Tell us more.
You can't even like use the same flop counter. like there's no guarantee that like like you can kind of get it to work today because like oftentimes we just call like a10.mm, but like if we like
what I want is like I want torch. So okay, so if I don't care about modularity, what I want is I want flop counter natively supported in torch compile, and the flop count dispatch mode just does some completely different path in torch compile that involves poking the scheduler for the flop count information.
Yeah, that's reasonable.
Any other comments, questions?
Also on the module tracking, it's not clear to me how that works with graph breaks. So in my head, we have like a torch function mode that tracks like which module you're in. And that way you can attribute certain performance and memory stuff that you find to whatever module you're currently in. And then if you compile, then I guess you turn off the module tracking mode and then we hit our compiled region. And then on exit, we like enter our new graph break region. And it's not immediately clear to me that all would just work, but I'm not sure.
Yeah, I will. Yeah, for the eager part, the mapping also needs to be taken care of. That's a good point.
But you said there's also a module tracking thingy that has hooks on modules that does that.
Yes. I think the question here is for us to enable torch compile, do we actually need to disable that hooks?
Okay, let me ask a more pointed question, which is, okay, so we didn't really manage to convince the room that AutoFSDP, like as originally scoped, was just kind of ambiguous whether or not we should do that or not. These things, these three like infra pieces, like, does anyone want to stand up and say, no, like I don't see why you want to do these things for compile? Okay, can we talk about how I'm going to use these to like do an auto solution? So Francesco, you were about to brainstorm something. Can we brainstorm that now?
Yeah. So my point was, if you want to have composability, for example, we want to provide a auto scheduler that's going to be able to reason across a number of different axes for parallelization. And we're gonna have to plug it somewhere in a solver or something that's gonna optimize a function, right? And in my opinion, FSDP can actually be decomposed as sharding across the weights dimension and activation checkpointing. But given that activation checkpointing is also part of fitting large models into memory, then the activation checkpointing policy is also going to be a function within your scheduler or your tuner. So if you basically just now have to decide which tensors you want to shard, which activation checkpoints you want to recompute matmos or that matmos or not, maybe that all gather. Well, now you're actually allowing for a more flexible alternative to just a frozen FSDP, which performs one specific thing, but instead you're allowing to mix and match sharding on 1 or 2 dimensions potentially, plus recomputing matmos or the all-gatherers, plus potentially flipping things around and so on. And I think this actually reduces the complexity of the optimization afterwards, even though it's not going to be looking into those parameters at the per module level, but instead at a per parameter level. So now the optimization or the decision happens at per parameter level, per tensor level. Is it clear, by the way?
It sounds like this is like assuming full compilation, right?
Well, this does assume, I think the only problem actually with distributed is that we want to be able to move some types of operations across graphs. That is the main concern. And those operators, they are basically running even on a separate stream or something else. But yeah, that was basically assuming full graph. If there is a way of moving those special ops, which are the comms ops, with cross graphs, I mean, it would be kind of fine.
Wait, let me ask you a more pointed question, which is, do you know what to do given Francesco's description, or no? Like you like it sounds nice, but the next step is not clear.
I think it's an extension of the simple FFDP. So shard every parameters and make decision and do the optimizations later.
Actually, even the sharding can actually be part of the decision, right? It's a matter of which parameters you want to shard and on which axis, and you can plug that into a function that takes your model and returns you the sharding policy basically that you can then apply to the model.
I see. So yeah. So I guess for me to take actions, they actually quite critical. Like if we decide this has to work with full compilation, that's actually a critical decision for me to move on, because I do see like I don't see that day will come very soon with this direction to enable it in recommendation models, and that's really decisive for me.
Okay, let me try to so we talked a little bit about how things could work in eager mode. So okay, so here's a straw man. The straw man is this. In eager FSDP, there is a part of it that is making decisions about sharding. Francesco, I know you care a lot about activation checkpointing, but I'm just going to ignore that for now. Sorry, it's just easier, right? So FSDP has to make some decisions about sharding at the beginning, and sometimes it can't. Eager FSDP can't do a good job because it just doesn't know the future. Okay, so the model we have here is that all right, I'll give you two variations. So model one is somehow we generate a thing we feed into eager FSDP that is just exactly what sharding planet should be, and something has produced the sharding plan, and you can figure out how to produce it, but like once you produce it, you go ahead and feed that into eager FSDP, and then that is your that is quote unquote AutoFSDP. AutoFSDP is just, some oracle which produces you the sharding result. The other variation is, well, you just analyze the eager FSDP algorithm and you're like, okay, well, here are some places where it would have liked some knowledge from the future, and you log that knowledge from the future, but it's much more of an FSDP specialized thing, which is just that I'm logging some information that FSDP can make use of to make better decisions when it's sharding. And that's it. That's all you're getting out of AutoFSDP. And once again, how I actually get that info, not specified. Like, that's just sort of a black box. Is that actionable? Is that different from what you were proposing here?
I think option 2 definitely sounds like I feel it's like a simplification. It's just the how part. But directional wise, I think it's a simplification. Yeah.
Well, then asking Francisco, Jansel, Harris, like, does this version of AutoFSDP like solve the things you were worried about?
I mean, if we are considering just, I think the AutoFSDP is gonna be basically how many blocks we're gonna be putting together, right? Is it gonna be 1 block, 2 blocks, 3 blocks, n blocks? Because those blocks are all consecutive anyway. So it's basically just, if you assume your model is a sequential of blocks, potentially the same blocks or different blocks, it's just how many of those, how you're splitting your list into consecutive chunks.
Okay.
If you assume there is like a repeated structure on your model, which is generally the case.
That's for llama model. So the strongest person who acts for this is recommendation model. So it's usually like a DAG, like instead of like repeated blockers.
But if it's a DAG, then can we actually assume or estimate properly the peak consumption given that things can run in parallel?
They don't actually run in parallel, right? It's just you have a lot of latitude in choosing how you interleave them. You need to pick a top sort for the DAG.
Yeah, need a top sort. Yeah, topology sort to have a order.
So let me make variation 2 even more concrete. So essentially, the info that you would feed to the eager FSDP bucketing algorithm is literally this module uses this much memory and this many flops and this much memory bandwidth. Like you get those 3 numbers for every single module in FSDP.
Yeah, and we know the pre-order, pre-forward order, post backward order. Yeah.
I personally liked your like explicit bucketing instructions better because that feels like, if I want to go if the automatic thing does something wrong, like it gives me a way to like copy and paste the output of the automatic thing and start hacking on it. While if I'm feeding in like hints, then like what if the algorithm does something wrong? Like I need to like lie about the hints and hope that the algorithm starts doing the right thing. But like how do I like know how the hints translate to the algorithm doing behavior? It just seems hard to hack on.
Where do you buy this? Do you know what to do given this preference?
That I think that kind of fall back to the original plan. Have a policy to be separate from the runtime to the current proposal.
Okay, so then let me just restate the current state of the plan for everyone to agree or disagree. Okay, so what we call AutoFSDP, let's not call it AutoFSDP. Basically, FSDP has a way for you to pass it a file that is the bucketing decision for everything. We'll figure out how to make it readable and editable, and it has to make sense. Okay, somehow we produce this file. Now, Wei is welcome to go off and do whatever he likes to like create a system that generates this file. From the purposes of the PD2 developers, that system is a black box. We don't have to care about maintaining it. They might ask us for some help, like, hey, we need a way to like do analysis on a model without actually running it for real, so that we can get out information that we can feed our black box. Sure, we can like deal with those on a case-by-case basis. But the black box sort of is like, its own system that we don't care about. Can we, or do people want to ship this? Does this organizational separation make sense? And to generalize for Francisco, like we would also have some file which tells you exactly what the activation checkpointing you do is.
All that done on Eager?
No, there's a black box that happens offline. So by the time you get to running your model, everything has been decided. And you're just like, the Eager mode code knows how to take in this info and then like act accordingly. I don't even know how you're going to do SAC this way. It depends on how Eager activated checkpointing works. Maybe that's just like something that only compile gets to do.
Yeah, I mean, without understanding a bit better the model in question to see how they could benefit from it, I don't know for sure. But by looking at models like Llama and so on, there are actually multiple axes, and depending on how you scale, the trade-off changes, and you might want to go from one thing to the other. So yeah, I don't actually know if like deciding on the FSDP boundaries is actually that. It can be annoying, but yeah, without knowing more about the model, yeah, I don't know the specifics here. But I'm gonna dig into the model.
Wei, Jansel, any last thoughts?
Yeah, I think that seems reasonable. I think we should work pretty hard to make this format like understandable by a user, so that but both so that like users can hack on it directly, then also
I
we
think lost Jason.
that same format.
Jansel, we lost you. Can you repeat after both so that users can hack on it directly and
also so that like there can be third-party tools that like do the scheduling heuristic. Like I think it would be cool if like someone not us could go and build one of these scheduling heuristics.
all right, so
But
turning it back
isn't
to
it a
you,
bit
Wei.
tricky? But isn't it a bit tricky if we mixture compile and the eager at the same point in here for those scheduling heuristics, given that the compile might change in the future, and then you might need to update your scheduling heuristics potentially or so on. I don't know.
Yeah, these schedules are going to be very brittle, and they're going to, if you update your model, then you're going to need a different schedule.
Or even your PyTorch, right? Because the fusion boundaries might change and so on.
Yeah, that's right.
Yeah, I think the contract of having the FSDP policy as a black box and a file and to be parsed in the later stage, I think that's a good contract. It aligns with my mental model.
Okay.
Right. Any final comments? Okay, let's ship it. Thanks, everyone.